For the first thing we're going to do in this video, we are going to derive the strength of the magnetic field inside a toroid. Now, a toroid is basically just a solenoid in the shape of a donut. So what we do is we begin with a solenoid over here, and we are going to just wrap it into the shape of the donut by connecting the two opposite ends. So if I take these two ends of the solenoid and I wrap them together so they meet each other, I then would have a shape of a donut. So I would have something that looks kind of like this. Now all the windings of these wires are going to be wound around in the shape of a donut. So we would get something like that. Now, in this case, instead of this current through the solenoid flowing along a cylinder, the current is wrapping around the outside surface of a donut. So the wires near the inner ring of my donut will be more tightly packed than the wires around my outer ring of the donut. And our question is going to be, how do we find the strength of a magnetic field inside the interior of this donut? So over here is a cross section of the donut. And the way I drew this picture, I have the current is flowing out of the board if you're near the outer edge of the donut. That's the circle with the dot. And the current will flow out of the board. It'll come out, it'll wrap around and flow into the board near the interior, near the inner hole of the donut. So the current is flowing out of the board and into the board near the center. Then it reaches behind the board and goes behind and comes out again. Now, if I use the right-hand rule, I could find the direction of the magnetic field somewhere inside due to one loop of wire. So this one particular loop right here and here, I could curl my four fingers, and when I curl my four fingers, if I am near the outside of the donut and my fingers are coming out of the board, if I'm near the interior of the donut, my fingers are going into the board, and I find the magnetic field is always wrapping around the center of the donut. So in this case, the magnetic field will be encircling inside the donut in a clockwise direction. So this is the direction of the magnetic field. Now, I only considered this one particular ring of current right here, but immediately next to it, there is another ring, and immediately next to it, there's another ring. So even if the magnetic field were to diverge, there's going to be another current to kind of kick it back in line. So the magnetic field will be circling around the inside of the donut. Now, if we say this solenoid has capital N total loops, well, then that means the toroid, the donut, will also have N total loops. So N is the total number of loops. Okay, so how are we going to actually find the strength of the magnetic field inside this donut? To do that, we're going to employ Ampere's law. So Ampere's law states that if I take many steps and travel around a closed loop, my B parallel times delta L is going to be equal to mu naught I enclosed. Now, when we work with Ampere's law, we are allowed to use any loop we want. There is no restriction on what loops we are allowed to choose. As long as we walk in a closed loop, we're okay. In practice, some loops are much easier to work with than others. Usually, as a rule of thumb, if your closed loop that you walk is either parallel with or perpendicular to the magnetic field, that's probably a good choice. No guarantee it's always the correct choice, but that is a good first place to look. So in red, I drew the magnetic field. I'm going to draw the direction of the path that we walk in purple. So let's choose to walk around the inside of the donut. So we're basically going to walk in a circular path around the inside of the donut. and this is the path that we're walking. Now, when I work with Ampere's law, there are two vectors in that problem. One vector is the magnetic field vector that is set up by nature depending on the currents and whatever else is going on in the problem. The other vector is the size and direction of the steps that I take as I walk around my closed loop. These vectors I am free to choose. As I said, I'm free to take any loop at all. Usually, if you're perpendicular or parallel with a magnetic field, that's going to be a pretty good choice. So I chose to walk in a circle around the center of the donut. The magnetic field is a circle around the center of the donut. So basically, I chose that my path will be always along this magnetic field. So my closed loop I chose here. My closed loop that I chose is aligned with the magnetic field. Again, I'm not required to choose it, but I wanted to. And it's going to end up being the easiest case to work with. And also, as I said, there are two vectors in this problem. There is the magnetic field vector. What component of the magnetic field is parallel with my step? That's B parallel. In a previous video, we called this B parallel B cosine theta. It doesn't really matter which we use. And I have the magnetic field and my step. I'm only free to choose my step. Okay, I look at this picture and I realize the strength of the magnetic field is going to be the same no matter where you are in the toroid in terms of where you are around your loop. Because if I spin the toroid, it's going to look the exact same. I'll still have a wire around me. I'll still have wires curling in the same direction. So if I change my position on the loop, I expect my magnetic field to be the same everywhere. So I could articulate that as saying, because of symmetry, I expect the strength of the magnetic field to always be the same. Around my path. Which I drew in purple. Let's take a moment and look what we have. We chose a path that is around the center of the donut through the inside. We are allowed to have any path we want, but some paths at the end of the day are more convenient to work with than others. We also have a magnetic field. The magnetic field wraps around the inside of the donut. Symmetry is a very powerful tool in physics, and you could convince yourself that if you were to imagine that you spin the toroid by some angle, you would still see the exact same thing. You would still have current wrapping around the toroid. You would still have a magnetic field wrapping around the toroid. So you really wouldn't see any change in the picture as it's drawn. So what do we have for the left-hand side of Ampere's law? So this B parallel delta L summed over a closed loop. This was written originally as the sum around a closed loop is B delta L cos theta. But then we said the B cos theta, we could write that as B parallel. This is basically the component of the magnetic field that is in the same direction as our step. So this is really equal to sum around a closed loop of B parallel delta L. And the magnetic field, we said, is the same strength everywhere along our path. If the magnetic field never changes in its strength, then I could, if the magnetic field always has the same strength along our path, I could think of this as being equal to B parallel times the sum around a closed loop times the size of our steps we take. Now this term around the closed loop, this sum, is just going to be the total path we take. The sum of all our steps is equal to the total path that we walk. The magnetic field has the same strength everywhere along our path, so I'm able to factor the magnetic field outside of the summation sign. If you don't really like how this looks, you could think of this as being equal to B parallel times the size of step 1 plus the size of step 2 plus on and on to the size of our final step. And now you could see very explicitly that B parallel would just factor out anyway. And well, what's the total path we walk? The total path we walk is just the circumference of a circle of radius r. So the total path we walk is then equal to B. B is the strength of the magnetic field. The magnetic field is entirely in the same direction, so B parallel is the full magnetic field, times the length of the path we walk, which is just 2 pi r. Okay, so the strength of the magnetic field is B parallel. There is no perpendicular component of the magnetic field. So the left-hand side of Ampere's law just becomes B times 2 pi r. Now what about the right-hand side of Ampere's law? The right-hand side of Ampere's law, mu naught, is a fundamental constant of nature, so I am not going to dare touch it. How much current do I walk around? Well, I walked around n total loops, because if you think at the beginning of this video, we said we took a solenoid. So here's our solenoid, and then all we did was this solenoid had n loops, and we just wrapped it around itself until it formed a donut shape. So if I wrap around my solenoid to form a donut, I still have n loops wrapped around the donut. So in total, I walked around n loops of wire. So I could write I enclosed as being equal to n times I, where I is the current in one wire, and then I have n wires total. So if I take this equation and rearrange it for the value of the magnetic field, I could say B is equal to mu naught Ni over 2 pi r. And this, where n is the total number of loops, I is the current, r is my distance from the center of the solenoid, from the toroid, and at that point I have the strength of the magnetic field inside a toroid. In this final example problem, we are asked about the torque on a square loop of wire. The square loop has a width of 4 centimeters and a height of 5 centimeters. And the square loop is placed in a background magnetic field as shown with 0.25 Tesla strength. And there is a current of 3.2 amps flowing around it in a counterclockwise direction. Now, from 121, we said acceleration is caused by a force. So force causes a change in your linear motion. Torque causes a change in your rotational motion. So we had the equation torque is Rf sine theta. So in this problem, we have a current flowing in a counterclockwise direction of 3.2 amps. So presumably there will also be a current flowing up along this segment. There will be a current flowing through this segment. Then the current will be flowing down and to the right. And we also said all the stuff down here, we don't really care about what goes on there. So the way I'm going to think about this problem is I'm going to divide the loop of wire into 5 segments. I'll just label A through E. So the very first segment of wire, I will call segment A when you're moving to the right and on the bottom at the very beginning of the loop. Then the vertical segment I'll call B, C, D, and E at the very end. And like I said, we don't really care about anything happening down here below the loop. So I see right away that there will be 0 magnetic force on segments A, C, and E. So segments A, C, and E feel 0 magnetic force. And the way I'm able to see that very quickly is we had F is equal to ILB sine theta. And if theta is equal to 0 or 180 degrees, that implies sine of theta is going to be equal to 0. And as a result of that, the force will be 0. Theta is the angle between the direction the current flows and the direction of the magnetic field. So here in segment A and E, the current is parallel with the magnetic field, so the angle is 0. In segment C, the current is exactly opposite the magnetic field, so in that case we have 180. In both cases, there is no force on segment A, C, or E. So only segments B and D will feel a magnetic force, and as a result of that, from the equation we're given from 121, only segments B and D will actually feel a magnetic torque. So what is that going to look like? Okay, what is the magnetic force on segment B? So for segment B, I could say F is equal to ILB sine theta. The direction of the current is straight up towards the top of the board. The direction of the magnetic field is to the right, so that is 90 degrees. So I could say the force on segment B is going to be, current is 3.2, the length of the segment is 5 centimeters, 0.05. The magnetic field has a strength 0.25 Tesla, times the sine of 90 degrees. Sine of 90 is just equal to 1. So I find the force on segment B is going to be equal to 0.04 newtons. Now, what direction is the force on segment B going to be pointing? To find that, we use the right-hand rule. So if I raise my arm in the direction of the current flowing, so my arm will be raised upward, I want to curl my 4 fingers in the direction of the magnetic field. To do that, I have to rotate my arm. Now I can curl my 4 fingers in the direction of the board. And when I do that, my thumb is, I curl my 4 fingers to the right. And when I do that, my thumb is pointing into the board. So the force is pointing into the board. And because I'm specifying a direction, I have a force vector now. So the direction of the magnetic force on segment B is into the board. I'm going to do the exact same thing for segment D. So segment D, to find the strength of the force, I do the exact same thing. We have the same current, the same length of the segment, the same magnetic field. Again, D is down and B is to the right, so they're still perpendicular. So segment D will have all the same numbers. So I could say the force is again going to be 0.04 newtons. For the direction of the force on segment D, I could point, now I will point my forearm downward. I curl my fingers in the direction of the magnetic field to the right, and my thumb is pointing out of the board. So the force on segment D is going to be out of the board. So the force on segment B was in, the force on segment D is out. So I'm saying force on B, force on D. Well, what happens if I take a object and I push, one side of the object is pushing out of the board, the other side of the object is being pushed into the board? That object will tend to begin to spin. So the left side of this loop is going to be spinning in a manner that comes out towards you. The right side of this loop is going to be spinning such that it rotates away from you. So there will be a torque on these objects. So I could say the total torque on the entire loop, so the entire total torque is going to be given as tau net is equal to torque from segment B plus the torque on segment D. Now, if I push on segment B into the board, it would tend to spin this way. If I push on segment D so that it comes out of the board, it will tend to spin in the same way. Because both forces tend to get the loop of wire to spin in the same manner, I'm going to add the contributions of the torques. What I said just now is the exact same idea as if I push in a certain direction and you push in a certain direction that is the same as me, then we would combine our forces. If we were to push in opposite directions, we would be taking the difference of our forces to find F net. In this case, the forces are both trying to rotate the loop in the same manner, so I'm adding their contributions together. So for the torque, I will say, okay, we'll say R is this distance from the center of rotation. So R could be the distance from the center of rotation. So here is my R. R is going to be 2 centimeters because it's from the center to the edge. So I could say tau net is going to be 0.02 for R. We found F was 0.04. And in this case, from torque, the angle that we take here is the angle between a vector connecting the center to the location the force is applied. So the angle between R and F. R is pointing to the right, F is pointing into the board, so that is 90 degrees. So I have sine of 90. This is the torque from B only. The torque from D is going to look very similarly because I could say plus 0.02. The distance from the center to the location where wire D is located is again 0.2 meter. The strength of the force on wire D is 0.04 Newton, and the force is out of the board. The vector from the center of the loop of wire to where the force is applied is to the left, and this is 90 degrees again. So again, I have sine of 90. So this is the torque on wire B. This is the torque on wire D. I combine both of their effects and I find the net torque is going to be 0.0016 Newton meter. Now, if you're worried about torque, because that was something we covered quickly at the end of last semester, when you're actually in an exam, the goal of a good exam is to test the material the exam is covering. So this problem involved finding a magnetic force, and then we had to recall something about torque from the previous semester. We did not cover torque very heavily in this one course in 122, so I will not ask you anything too intense on torques when you take your exam. The exam is going to primarily be focused on ideas from magnetism and electromagnetic induction that we have been covering for a while now.